Hi guys, what we're doing today is we're looking at RP8, which is to do with wave speed, frequency and wavelength. So this is one of the RPs, the required practicals in the AQA course. There's this detail here that's given in the specification. It says you need to identify the suitability of apparatus to measure the frequency, wavelength and speed of waves in a ripple tank and waves in a solid, and take appropriate measurements. So this is what they're on about. So hopefully your school should have one of these. This is called a ripple tank. It's basically a big table full of water. Sometimes it might look like this one here or this one here, but they're all the same thing. Essentially, you've got a tray of water there and you've got something that oscillates up and down. So here there's an electric motor. It oscillates up and down and it causes this bar here to move up and down. And when it moves up and down, it creates ripples in the water. Now this one here actually has two dabbers, so they go up and down and they'll create ripples that look like that. This one here, you can see it has a bar. You can put other things in the water as well. This person's put some plastic things there, but it's not relevant for what we're doing. You'll also notice that you've got a light source up here, and with this type the light will come down and it will shine through, and the pattern that's made will be projected down here. If you go on like this, the light shines down and there's a mirror just behind here and it's projected onto this screen here, so you can see the wave pattern. So what you're going to be able to do is you're going to be able to use this equipment and you're going to be able to measure three things: the wavelength, the frequency and the wave speed. So let's have a look. Now if we start off with wavelength, now the easiest thing to do is just to get a ruler. But there's a bit of a problem. First off, we're talking about the suitability of using different measuring equipment. We've got two different rulers here. Which one would you use and why? The answer is you'd use this one. This ruler is better because what we say is it's got a higher resolution. That means the smallest thing you can measure is lower, i.e. in this one, the smallest thing you can measure on the scale is 1 millimeter. So you might be able to measure half a millimeter if you can go halfway between. On this one, the smallest thing you'd be able to get is halfway between 89 and 89.5. So the resolution on this one is 0.5 millimeters, and the resolution on this one, 0.5 centimeters, and the resolution on this one, 0.1 centimeters, i.e. 1 millimeter and 5 millimeters. So this ruler would be good to use because it has a higher resolution. The detail you can measure is much smaller. So seems simple enough. All you do is you get a ruler and you measure the length from one wave to another, right? So there to there, that's about 5 millimeters. Bit of a problem. The first problem is, isn't there something wrong with this diagram? Because normally these waves are moving. So if you want to measure it with a ruler, you've got to get them to stop. So how do you do that? Well, one thing you could do is take a picture. Now, if you're going to take a picture, you need to do like I've done here and take a picture with a ruler in it. Otherwise, the scale will just all be messed up. The second thing to do is you can get it to appear to stop. Now, to do that, you need one of these things here. This is called a strobescope. This is a light that flashes at a certain frequency. In fact, it flashes at the same frequency that this oscillates. The effect is the waves appear to be stationary on the screen over here. That's one thing to use. You may not have one of them. There is a disadvantage with stroboscopes, which is to do with safety. If you have someone suffering from epilepsy, for example, it can cause fits or seizures. So they're the two things you could do for wavelength. Another problem is accuracy. I've measured there and I said it's about 5 mil, but actually it's probably not. We're not very accurate. Accurate means you're close to the real answer. So what would be the better thing to do to get a more accurate answer? Well, the best thing to do would probably be able to measure from one part to another. So I'm going to go from there to there maybe, and I'm going to count how many waves I've got. Now just remember, that's one wave. So one wave, 2 waves, 3 waves, 4 waves, etc. 5, 6, 7, 8, 9, 11 waves. So What we can do is we can take the distance. Well, that distance there is 0.5 divided by 5. It's about 5 centimeters, 5.0 centimeters. We said we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 waves. So what we need to say is that 5 centimeters is equal to 11 waves. So how much is one wave? Well, if 5 is equal to 11, I need to divide this number by 11. I should get my answer, which is 0.45 centimeters. See what I mean? I said earlier, I thought it was about 0.5 centimeters, 5 millimeters. Actually, it's 0.45. So you get a more accurate answer if you use this technique. You count more and you divide by the number of waves. Just remember, as I said, that there is one wave. So that is how you measure the wavelength. Frequency. Now if we go to this, so you've got to ignore this little bit here. It's because on this we have a change in depth. That doesn't matter. I'm just looking at these waves moving along. Now if you remember from the definition, frequency means either the number of oscillations per second or the number of complete waves passing a point in 1 second. So what we could do is I could say, right, I'm going to count how many waves go past a point in a second. Ready? 1. Yeah, it's not going to be very accurate. Human reaction time is between about 0.2 and 0.6 seconds. I mean, it depends on your age, what you do, etc. But 1 second, you timing, you're going to have so much uncertainty in your timing, it's just not going to be an accurate answer. So the best thing to do, something similar to what we did with the wavelength, is instead of just counting 1, we're going to count more than 1. So what we're going to do is we're going to count for maybe 10 seconds and see how many waves we get. So what I'm going to do is I'm going to time 10 seconds, see how many waves you get. Go. Okay, I got in that one about 23 waves in 10 seconds. Frequency means how many waves you get in 1 second. So all you need to do is divide that by 10, 2.3 hertz, the number of complete wavelengths passing a point in 1 second. Wave speed. Wave speed is very similar. There's 2 equations to work out wave speed. The first one is one that you've come across in the previous session, where we're doing wave speed is frequency times wavelength. So if we take the frequency and the wavelength from what we've just measured, then surely we'd just be able to get that done. Just multiply the frequency by the wavelength. But what if you haven't got them? Well, what you could do is this. You could use another equation that we've had before. You could use speed is distance divided by time. So what you need to do is you need to measure out a set distance. So maybe I'd say from here, there's my start, to here is my finish. Now what I'd do is I'd get a meter rule and measure the length there on there. That's a meter rule. And all I'd do is I'd go, right, when this wave goes past the start point, I start the stopwatch and I time how long it takes to get to the finish line. I then just take the distance and divide it by the time. Now, as I said, we're going to have some inaccuracies with your time measurement due to human error, due to reaction time. The best thing to do is make this distance as long as possible. If you make that distance as great as possible, your time is going to be longer, therefore you're going to reduce your uncertainty. What I would do though is I wouldn't make the distance, I wouldn't start it from somewhere like here. I'd give myself a bit of a head start so I know when the waves come in so I can get ready to start the stopwatch. Okay, the other experiment is to do with measuring waves in solid. This is the usual one that comes up called Mels Experiment. So this thing here, the setup is you have a string. The string is connected to this thing. This is an oscillator. So it's usually an electric motor that goes up and down and causes a wave to travel along the string. The string at this end over here is at a fixed end. Either it'll be tied to something or it's wrapped around a pulley here with a mass on it to create tension. Now what will happen is you'll have this connected to a signal generator, this oscillator. This signal generator provides an alternating current which tells the oscillator to oscillate, to go up and down. This number here will tell you the frequency that it's oscillating at, therefore the same frequency as the wave, because remember, the frequency of the wave is the number of oscillations per second, or the number of complete wavelengths that pass a point in 1 second. So that's your frequency. The wavelength's a bit tricky because here it looks like you've got 3 peaks, but it's not really the case. This wave is continuously oscillating, and what you're looking at is a sort of, not a freeze frame as such, but you're looking at the maximum of the motion of the string, i.e. going up and down. So this is what the string's actually doing. It's going like that. On the other diagram, you've got that and that shot in one. So what you've got to imagine is that this here is what the string is doing at one time. And then when it's done oscillating, it's then doing this. So if you look at that, if I just draw this without there, very badly, that there is what the wave pattern looks like. That there is one wave. So what we do is this. Just get rid of this for now. So the distance from there to there, that is one wave. The distance from there to there, that there is half a wave. So if you look on here, we have got 3 halves of a wave. So that is 1.5 wavelengths worth. Now if I said that the distance from the oscillator to the pulley was 150 centimeters, and you want to work out what the wavelength is, you'd say 1.5 waves is 150 centimeters. Okay, 150 divided by 1.5 gives you 100 centimeters. The wavelength is 100 centimeters, or a meter. Now the final thing is wave speed. This is a bit of a different type of wave that you're seeing here. This is something called a stationary wave that we do in A level. Because here is the wave that's going in that transfers energy, but once it interferes, it produces this wave pattern. And this wave doesn't appear to be going anywhere. So when we're working out the speed of a wave, what we're actually doing is we're working out the speed of this wave now that's coming in. You will see it for like a tiny amount of time when you start the experiment. Now it's very difficult to measure the wave speed of that by eye, so all we do is we use this equation. Wave speed is frequency times wavelength. We know the frequency because we just need to look at the signal generator here. We've worked out the wavelength by saying that there is half a wavelength, therefore we've got 1.5 wavelengths. So all we do is frequency times wavelength to give you the wave speed. Hope you enjoyed. See you next time.